So let's go ahead and solve this problem. We have a power plant. It operates as a regenerative vapor power cycle with one open feed water heater, and here's a layout. And I know that I've given you the layout, it's in the textbook, but you should be able to work through this layout and really understand it. Let's take a look at what we have. We have a steam generator, then we have a first turbine stage, and then a second turbine stage. Then we have a condenser, then we have one pump, the open feed water heater, and then the second pump. And so I know that they give us information about pressures and temperatures, etc., but let's walk through this cycle. So what do we have here? This is state 1. State 1 is what leaves the steam generator and enters the first turbine stage. After the first turbine stage, we have state 2 of the steam, and that's 2 can be diverted. Some of the steam is diverted after the first turbine stage and comes down and feeds this open feed water heater. That's going to be high temperature, high pressure steam. The rest of the steam continues to the second turbine stage and expands to a lower pressure at state 3, which then it goes into the condenser, comes out of the condenser because it's going to be fed into the pump. This is our standard saturated liquid going out of the condenser and into a pump. Then it's boosted, it'll be compressed liquid at state 5. It's mixed with the steam coming from state 2 in the open feed water heater, so there's 2 ins, inflow and inflow, and only one outflow, and outflow at state 6. Now at state 6, because it's flowing into a second pump, we would like that to be saturated liquid, and that really dictates the condition of the steam at state 6 dictates how much is diverted after the first turbine stage and down to feed the open feed water heater. But let's continue now, and we go to state 7. It'll be compressed liquid. That's our last state, and then it goes through the steam generator and continues in the loop. This diversion or splitting is quantified by this Y. This term Y right here. Let me change the color maybe. Put that Y. So Y is a mass fraction that went through the first turbine that gets diverted down to the open feed water heater. Maybe it's 20%. Maybe Y is equal to 0.2. What does that mean? 20% or 1/5 of the flow going through the first turbine goes down to the open feed water heater. If it is 20%, then 1 minus Y would be 80% as an example, and that would be what is the fraction of the steam that continues through the second turbine, through the condenser, this is 1 minus Y, through the pump, and that's 1 minus Y, which then joins back into the open feed water heater. Well, once it joins back into the open feed water heater, it's basically back to 100%, and that's why they put this 1 here, and that's what goes into the steam generator, and then 100% going out of the steam generator into the first turbine stage. One way to think about it is you say the steam entering the first turbine stage, that's as much as, they're the same flow rate as what enters the steam generator, which is the same flow rate as what enters the second pump. They're all the same m dots. But it's not the same m dot as to what goes to feed the open feed water heater from state 2. It's not the same as what feeds the second turbine stage, or what goes through the condenser, or what goes through that first pump. Those are all described by these Y, this mass fraction. If you wanted to, you could think about Y is the mass flow rate that goes down to feed the open feed water heater from, in between the 2 turbine stages, divided by the mass flow rate that went through the first turbine stage. Okay, that's confusing. Hopefully that helps. So we have our layout, we have our states, and we even have our mass fractioning, splitting and joining back together. Okay, then we take a look at, well, we're given some pressure and temperature of the steam at state 1. It expands down to this pressure. 1 megapascal is the pressure at state 2. And because it's an open feed water heater, the pressure at state 2 and the pressure at state 5 and the pressure at state 6 are all going to be the same. Just go back and look at heaters where you're mixing fluid streams, you're having two ins with one out. The standard assumption is neglect any pressure loss, hence they all have the same pressure. Okay, then the remaining steam expands through the second turbine stage down to 30 kilopascal. So now they're telling us this, the pressure here is 30 kilopascal. That's our lowest pressure. Well, you go through the condenser. What's the pressure at state 4? Well, our standard assumption about a condenser is it doesn't change the pressure. It's also 30 kilopascal. And then from 4 to 5, there's that pressure boost. That's the purpose of the pump. So it boosts it from 30 kilopascal up to 1 megapascal or 1,000 kilopascal. And then this pump here at state 6, it boosts it from 1,000, maybe I should write that like 1 megapascal. It boosts it up to state 7, which has the same pressure as state 1, which is 12 megapascal. So the pressure at 7 is 12 megapascal. Okay. Continuing to read the problem, saturated liquid exits the open feed water heater. That's our standard assumption. We talked about that. The net power output of the cycle is 330 megawatts. Okay, we'll make a note of that, W dot net. That's not what comes out of the first turbine only or what comes out of the second turbine only. It's really what comes out to total out of all of the turbines minus what has to go back and feed the pumps because we have a net power out. Okay. Assume that both turbine stages and the pumps have an isentropic efficiency of 80%. So a little more complicated than how do we handle those pumps and those turbines, but we can do it. And then it asks, calculate the thermal cycle efficiency. The answer is going to be 34%. What is that mass flow rate into that first turbine stage? And you'll see this wording. It's a little funny, but it's into that first turbine stage. What is that m dot into the first turbine stage? That's what they're asking us to find. And then, what is the rate of entropy production in the open feed water heater? Something like sigma dot for that open feed water heater, sigma dot. Okay. Well, the steps are get a good schematic, a good layout of the plant. Get all the states labeled, get all the components labeled. Get your mass fractioning symbols down like y and 1 minus y. Okay, we have done that. We've talked through it. The next process is to get a table of all of the properties. Now, once you have a table of all the properties, the key are the enthalpies, because once you have the enthalpies, then you get a table of all the energy transfers, all the Q's and the W's for each of the components. So we get a table of properties and a table of the energy transfers for the Q's and the W's. And once you have that, then it's simple to get the thermal efficiency and these other pieces of information. Okay. Now to calculate part C, the rate of entropy production, we're going to need also the S's for our properties, especially our properties that are surrounding the open feed water heater. We're going to need to know the S at state 2, the entropy at state 2, the S coming in state 5, and the S going out at state 6. We're going to need those three entropies, but otherwise the primary focus is on enthalpies. All right, so I'm going to leave this slide. Hopefully you have this in notes or can go back to it, and we're going to refer to it, but I can't jump back and forth. You'll just get dizzy with me. So what I do is I'll start right here, and what we're going to do is we're going to put together basically a table. So I'm going to go ahead and type, because my penmanship isn't that good, a table of properties. And so in this table, I like to put a little description, describe the state, and then I have a column for the state numbering, and that's pretty easy. It's like 1 and then 2, etc. But let's go back to that in a minute. And then I'm interested in the pressure as a property in kilopascal. Now I know that some of the pressures are given kilopascal, sometimes in bars, sometimes in megapascal. basically get them all into kilopascal and put them in all one column. And then the temperatures, we could put Kelvin, but it's common to use C in our tables for steam. It's all in degrees C. And then we don't use this column that often, but I like to put it, it's quality. Same for the specific volume, and the specific volume is meter cubed per kilogram. And then our enthalpy column, kilojoules per kilogram. And then our entropy column, kilojoules per kilogram Kelvin. Looks like I got an extra column, but that's okay. Now, you go and you have solved a few of these problems before, and you're going to go from the inlet of the first turbine stage to the exit. Well, they gave us an isentropic efficiency. Basically, we need to first do kind of a two-step process. And I like to talk about state 2 as if it was isentropic expansion, then use that isentropic efficiency to calculate the actual exiting steam conditions. That's why I call it 2 actual. And then likewise, for the second turbine stage, we're going to be expanding from 2 actual, that's the input, to 3 isentropic and then 3 actual. So that'll help us analyze. So we have 2 lines for state 2 properties as well as 2 lines for state 3, the isentropic and then the actual. And then coming out, we have state 4. Then we go into the pump, which is out of the pump. State 5 is compressed liquid. And then we come out of that open feed water heater at state 6, go through the pump, and we go out at state 7. The pumps we really don't need to have like 5S and 5 actual or 7S and 7 actual. You can see that. Now, we put in some of the information that was given to us. So it started out that state 1 had a pressure of 12 megapascal or 12,000 kilopascal, all right, and a temperature of 560. So it's like these 2 pieces of information fix the state. I could go and get specific volume if I need it, enthalpy if I need it out of the steam tables, and entropy. That's why I make a little note over here, a little description of what's going on. I say, look, I conclude that this is superheated, that's my notation, and that I really know pressure and temperature, and I'm going to go to our textbook table A4 and I'm going to pick out the properties of interest. So you don't need that note or that description, but it just helps me when I go through these problems. And so the quality's not applicable. I really don't care about specific volume, but I go and I get 3506.2, and then I get for the entropy 6.684. You could put another 0 there, another 0 on the end of the enthalpy as well, but there you go. You should be able to look those properties up out of table A4, knowing the pressure and the temperature. Now we think, how do we go from state 1 to 2S? Well, it's going to drop to 1,000 kilopascal or 1 megapascal. That's the pressure we know. And maybe I should finish out that pressure column because that's the same pressure, the actual versus isentropic pressure, so to speak. And then you drop, in our problem, we had a 30 kilopascal condenser pressure. That's the inlet to the condenser. This is the exit to the condenser. So those are all 30 kilopascal. Then we boosted the pressure out of the first pump all the way back up to 1,000. And then it came out of the open feed water heater at 1,000. And then out of the second pump, it boosted right back up to 12 megapascal or 12,000 kilopascal. So our pressures, we could put all those down. But we come over here and we say, at state 2, we're going to consider isentropic expansion. So if I wanted to, I just kind of copy this value and paste it right there. That's the same S. So I anticipate it's going to be superheated. What I do is, if you want, you can make an additional note. You compare that S with S of F. Is that S greater than the saturated, S of G, sorry, saturated vapors entropy at 1 megapascal? If it is, and it is, you conclude that this is superheated. And so now our pressure and our entropy fix the state, and we still stay in table A4 for superheated steam. So I like to, I don't need the temperature. I could work and do the interpolation to get temperature. The quality is not applicable. I don't need the specific volume, although I could interpolate and get it. I really need that enthalpy. And so that enthalpy, you can interpolate in the table. It's a little bit of work, yes. 2823.27. Instead of going blow by blow how to do the interpolations in the tables, I'm going to assume that you can do that so that I can get through this example problem in a short amount of time. Okay, now we sit there and we say, well, how are we going to use that isentropic efficiency? I like to put a little extra table down here or put it to the side, and you think about what is the work that the first turbine stage would have produced if it would have been isentropic expansion in the units of kilojoules per kilogram. And you look and you say, well, it would have been this 3506.2 subtract off 2823.7. So you do the math, and if it would have been isentropic expansion, you would have got 682.93 kilojoules per kilogram. But we're given an efficiency for that turbine. That efficiency, isentropic efficiency, is 80% for this problem, 0.80. So then you ask, well, what is the work that the first turbine produces actually? Is it the same? Is it greater? Is it less in kilojoules per kilogram than this 682.63? Well, using that efficiency, what you do is it's not going to produce as much. It's going to produce only 80% of that. So you multiply the 80% by 682, blah, 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 you get 546.35. And there is our actual work that the turbine produces, accounting for the isentropic efficiency. So you come up to this table again, and you say, no, it didn't go from 3506 down to 2823. It went a decrease of 546. So you take 3506.2, subtract 546.35. I don't need to write that out, hopefully, but you get 2959.85. Okay, so there's our actual enthalpy. Well, you can think that, hey, I have pressure and enthalpy. I'm still going to be in the superheated region, pressure and enthalpy. I still use table A4 to look up any other property that I need. I could, do interpolation to get that temperature. I could do interpolation of specific volume, but I don't need it. The one property I do need is the entropy S, because that's what's going into the next turbine. So you do the interpolation, knowing pressure and enthalpy in the superheated table, get S. That's 6.9558. Okay. Now, if you understood that, going through the first turbine stage, go to the second turbine stage, it's the same process. I'll do a little faster, 6.9558 if it's isentropic. We look over here and we say, well, we don't know if it's going to be superheated or not. We have to compare this S of 6.9558 and see if it's greater than S of G for this problem. And when we do that, we find that nope, it's not. It's less than S of G, the saturated vapor entropy at 30 kilopascal. Hence, we conclude that it's two-phase. So I like to go ahead and calculate that quality. That quality is 0.880897, too many digits, but there you go. Maybe I should review that equation very quickly, but I think you've got it. That the quality at state 3S is equal to the entropy at state 3S minus the S of F at 30 kilopascal, S of G minus S of F. So these are the saturated liquids entropy and the saturated vapor, and the actual entropy coming in is in between them, hence you get the quality. All right, good little quick review there. So once I have the quality, what I can do is I can use that to calculate the enthalpy. It's in the two-phase region, and we find the enthalpy is 2347.07. So over here in my discussion, it's two-phase. I know the pressure and the entropy, hence I get the quality and then the enthalpy. And I need to use table A3. That's our two-phase region with the pressure as the primary input to the tables. All right. Well, you then come down and say for our work of the second turbine, isentropic, in kilojoules per kilogram, what is that? Well, it's that difference between this enthalpy value and that enthalpy value. So these two enthalpy values, H2A and H3S, and we calculate 612.79. We have the same isentropic efficiency of 80%, so we find the actual work is 490.23. Very good. So you come up here, you take the 490.23, subtract it off the 59.85, and then you're left with, for the enthalpy at 3A, 2469.62. All right, same thing. You come over here and you say, well, we know the pressure and the enthalpy. We conclude it's two-phase. You just do a little bit of work and you find that the quality did go up. The quality is now 0.93336, but it didn't have so high irreversibilities that it kicked it out into the superheated region. And so we still use table information in table A3, and we then can do what I just did, get the quality and confirm that it's still in two-phase region. Now we really don't need this entropy S, but if you needed it, you could then calculate it. We don't need the V. We could calculate it if needed, but we need that H. Okay, let's take a look at state 4. Well, state 4 was what came out of the condenser. It's saturated liquid. Okay, and we know it's pressure, and so we just use table A3. I didn't leave enough room for that, so I'm going to just do sat lick. And then pressure, maybe I just put pressure A3. All right, there you go. And so you can look over here and get H of F, the saturated liquid's enthalpy at that 30 kilopascal. It comes in at 289.23. All right. You don't need the S either. Okay, now you ask yourself the question, how do I analyze that pump going from 4 to state 5? Well, I do it in 2 steps. I calculate the work for that first pump, assuming it's isentropic. And you say, well, what's the equation for that? It's our V times, I'm going to put dP, the change in pressure. So for this problem, I'm going to run out of room, but our V I need, so I come back here, right there, and I get the specific volume of saturated liquid at that 30 kilopascal, 0.0010223. All right, there you go. So that's that V that's needed right there. And then what's the change in pressure? Well, the change in pressure, you're going from 30 up to 1,000. So 1,000 minus 30, what is that? 970 kilopascal. And then you remember your units that meter cubed per kilogram times a kilopascal gives me this kilojoule per kilogram. So the units work out really nice. So what I'm going to do is I'm going to come down to this table right here, and I'm going to say multiply V times dP, watching your units for the first pump, and we find that the work, isentropic work, 0.9916 kilojoules per kilogram. Well, we have some isentropic efficiency for the pump given. It was 80%. So what should I do? Should I multiply by 80%? No, because it's a pump. You're going to divide by, it needs a higher work input to accomplish the same change in pressure. So when you divide by the isentropic efficiency, it's 1.2395. Too many digits, but there you go. Now, you would take that actual increase in enthalpy and add it to this enthalpy at state 4 to get the enthalpy that comes out at state 5. And so that comes out at 290.47. Okay, you do the same thing. I'm not going to put a label in here. I didn't have enough column entries. And you do the VDP. Well, first of all, I've got to get let me just back this up. State 5 is compressed liquid. And we basically used VDP to calculate it. VDP, if that fits. No, it doesn't. Too bad. But you got that. State 6, we look at it. Well, it comes out of that open feed water heater ready to go into the next pump 2. And so it's the same as state 4. It's saturated liquid, knowing that pressure. So we can go over here and say, okay, well, what's my H of F? Add 1,000 kilopascal or 1 megapascal, 762.81. Okay. We also have to get V sub F 0.00111273. Where did we get those two values? Out of table A3. And then we say, okay, what's my V times the change in pressure? Now this is a huge pressure change, a lot bigger than the last one, because we're going 11,000 kilopascal increase. And so our specific work, if it would have happened isentropically, comes in at 12.4003. With our isentropic efficiency of 80%, we really have to supply more work. We have to supply 15.5004, negligible on the 004, but there you go. So then we come up here and say, now I can get the enthalpy coming out at state 7. So you add the 15.5 with the 762.81, and you get 778.31. All right, this is the key column right here for the enthalpies, and we're pretty well done with the property table. Just because I know that part C of this problem asks for the entropy production in the open feed water heater, I need to get the S at state 2, and we did get that. That's right there. That's good. That S at state 2. We need to get the S at state 5, which is not in our table. We're going to have to do a little work there. And then we also need the S at state 6, which is going out. Well, that one's easy because it's saturated liquid, so I just get S of F, the saturated liquid's entropy. So that one for state 6 is 2.1387. So these we need to answer part C, and I need this one right here. Well, I have to do a little digression because it's really not easy to get that that entropy. But I would go back and recall TDS relations, and the TDS relation would be something like TDS equal to DU plus PDV, and there was a second TDS relation that we used, TDS equal to DH minus VDP. And this second one is the one which will allow us to estimate a small change in entropy, knowing a small change in enthalpy, a small pressure change, and the change in temperature, etc. Well, this pressure change is going to be big, but our V is constant in that equation. So you can do this. You can say my small change in entropy, or the entropy change, is my 1 over temperature times my DH, change in enthalpy, minus my VDP. And I'm thinking about going from the input of the pump, which is right here, to the outlet of the pump. Okay, I forgot to add that number. Let me do that right now. You can look up the saturated liquid's entropy S at state 4. That comes in at 0.9439. Okay, so what we want to do is we want to add a small amount to account for going through that pump. And you say, well, we already calculated what the change in enthalpy was going through the pump. Wasn't it our VDP divided by our isentropic efficiency of that pump? Sure. And then we have minus VDP in this equation. Then you divide by the absolute temperature. You have to put that in Kelvin. You can't leave it in degrees C. And so this is an equation to estimate the change in S. Okay, for this problem, if you run our numbers, because you have the V coming in, you have the dP, just like what we calculated, the isentropic efficiency, the temperature, the saturation temperature, I should have emphasized that. So saturated liquid at 30 kilopascal has a 69.1 degrees C. We add 273, and that's the temperature we put in this equation below. And when you calculate that change in entropy, or estimate the change in entropy, you find that it's like 0.000724 kilojoules per kilogram Kelvin. Again, I emphasize this is not temperature in degrees C. Make sure it's in Kelvin. Okay, so then we add that, and we can calculate then what is this S. I need that S at state 5, and we estimate the S at state 5 to be 0.94462, just a little bit greater than the S at state 4. All right, a lot of work to get that number, but that number is going to be needed for our entropy balance on the open feed water heater. Okay, well, I filled this table up, this slide up, and again, the most important is our enthalpies, and then we're going to use these entropies as well. Well, there's one more table that I like to put together, so let's go ahead and go to a clean slide. And this table is a table not of properties, but it's a table of energy transfers. What do you mean by energy transfers? Well, to transfer from each component to the surroundings. Well, how many components do we have in our system? Well, we have our first turbine, then we have our second turbine, and then we have our condenser, then we have our pump 1, or first pump, then we have our open feed water heater, and I'm going to come back and talk about that some more, then our pump 2, and then our steam generator. So those are all the possible components we have. And what do you mean by energy transfers? Well, we're going to put the energy transfer like a heat transfer in terms of kilojoules per kilogram. So it's per unit. It's a rate of energy transfer per rate of fluid flow through that device. So that's common notation. I'm going to leave a column blank, and then I'm going to come over here and I'm going to say work, comma, in kilojoules per kilogram. Actually, I should have added another column that I think about it, but that's okay. We'll deal with it. And I'm going to leave these two columns, the third and the fourth, or the third and the fifth column, blank for a minute. And now what we can do is we can ask the question, does that first turbine, is a standard assumption that it have a heat transfer with the surroundings? And the answer is no, it's adiabatic. So half of this table, or many components in this table, we can just say, oh, it's 0. Same for the second turbine. It doesn't have any heat transfer. How about the condenser? Oh, it's going to be a significant heat transfer, and because it's out of the heat transfer, I anticipate this to be negative. I'm just going to make that mental note. I'm looking for a negative number there. How about for the pump? No, they're adiabatic. How about for the open feed water heater? Well, it has heat transfer between the hot steam side coming in and the cooler liquid side coming in, but no with the surroundings. And then pump, and then the steam generator is going to be a large positive value. So what I have is I have a bunch of zeros in this column and only two values. One is going to be negative, one's going to be positive. Let's go ahead and do what is the equation for this steam generator? Well, we're bringing it in at state 7, taking it out at state 1, so it's the enthalpy at 1 minus the enthalpy at 7. Now, if you come back and you work with what is for the condenser, maybe I should have spelled that out, condense, condenser. All right, that's going to be our enthalpy going out at 4 minus our enthalpy coming in at 3. And yes, by doing it that way, it will be a negative value. Okay, let me leave these as symbols for a minute and then come over here for a minute and work on the works. So this work out of the first turbine, that's going to be positive. How about out of the second turbine? I expect a positive answer. What about the condenser? Does it have any shaft power in or out, any work transfers? No, it's 0. How about our pump? Well, that's a power consuming device. This should be negative. And then our open feed water heater, no, there's no shaft in or out. Likewise for the second pump, it's negative because it's into the device, and the steam generator has 0. I think if you get the, it's like, I know what I'm looking for, it's positive or negative, or it's 0, that really helps. Now, if you go back and you take a look, what would be the equation for that specific work out of that first turbine stage? Well, it comes in at high enthalpy 1, and it exits at low enthalpy 2. That'll be a positive enthalpy change, a positive work per unit mass. How about for the second turbine? It'll be our H2 coming in minus our H3. That'll give us our positive work there. Now, this one's a little tricky, but look, we already did all the work for the pump. We already found that that first pump is 1.2395, whatever, too many digits, kilojoules per kilogram. I just have to remember that it's negative. It's not a positive work from the perspective of the system. It's back into the system. All right, and likewise here it's a negative, and we already did that work. It's a 15.5004, something like that. Okay, so now you have to ask the question, well, let's go ahead and substitute numbers and then take a look at these magnitudes. So for that condenser, we are going to get negative, I'm going to emphasize that by giving a space there, 2180.39. All right, and then when you go and compute for the steam generator right here, you're going to get a positive, maybe I emphasize it with a plus, and it's a 2727.89. Good. We come up here for a first turbine, and it's going to be a positive. That first turbine, actually we already did the work on that too. It's 546.35, and it's, this one is 490.23. So the bottom line is we could have left all of this open feed water heater out. We didn't even need to put it in here because it doesn't have any energy transfers with the surroundings. Okay, that's one thing. The next thing is we want to do a sum or a net, and this is the bottom line. When you take that column of Q's and you sum them, you'll get our Q net. And when we do it here, we get 547.50. And likewise, when we come over here, we get 1019.84. And a lot of students will think that our Q net and our work net need to match, and they don't match. They're not the same magnitudes. And then they'll say, well, something's wrong. And it's because it's per kilogram for what goes through that component. And a kilogram that goes through the condenser is not the same as a kilogram going through the steam generator. And so maybe what I should have done is I should have said, what is the mass flow rate at a different column that goes through that component, our component of interest, divided by the mass flow rate that goes through that first turbine. Okay, so I take a look at the first turbine. That's easy, it's 1. How about through the second turbine? No, it's 1 minus y. See, that's our 1 minus y mass fraction. How about through the condenser? 1 minus y. How about through our first pump? 1 minus y. How about the open feed water heaters? No, should have left it out. The pump, the second pump, is back to 100%, and then the steam generator is back to 100%. So I like to introduce another column, and that other column, I like to put it as Q asterisk. I know the book doesn't do it, but I'd like to do it this way. And it's in kilojoules per kilogram that goes through that first turbine. Likewise, you say, I want W asterisk, and it's like a work, but it's not on per kilogram that goes through the component, but it's on the kilogram that went through the first turbine stage. Kilojoules per kilogram that goes through the first turbine. Now, if I get these Q asterisks and work asterisks correct, then I can get the net down here and they'll match. It'll be a good match. Okay, so we don't, all these zeros are still zeros, but when you come here, it's like I take my, let me just write it out down here, my Q, and I look at my units again, kilojoules per kilogram that go through the component, and I multiply by this m dot that goes through the component divided by the m dot of the first turbine. So then I would have the kilograms divided by the kilograms for the first turbine. They cancel, and so great. So basically I take this value right here, and I have to multiply by 1 minus y. And I should have emphasized that once you have all your enthalpies, you can calculate what is the appropriate mass fraction y that needs to be diverted. What is this mass fraction y that needs to be diverted? And I thought I did that already, but I don't see it up here. And so let me come back here and do it. You do an energy balance for this control volume around the open feed water heater. And so you're going to get that the y, which is our mass fraction, coming down from state 2, bringing with its enthalpy. And then we're going to have another n, which is our 1 minus y, bringing with it the enthalpy at 5. And then it goes out 100% back to 1 for the mass fraction, enthalpy at 6. So y is the only unknown in this equation once you get all the enthalpies. Let me do it in 2 steps to avoid algebraic errors. H2 minus H5 equal to H6 minus H5. Hence, y is equal to H6 minus H5 divided by H2 minus H5. Professor, I get this question all the time. Do we have to memorize that? No, I don't recommend you memorize it. I just recommend that you know how it was derived, because it didn't take us too long to reestablish an equation like that. And then what happens is maybe the next problem does something a little different, and then our numbering system changes, and so it's not state 2 coming in or state 5 coming in, and so then if we just memorized an equation, it wouldn't help us that well. So anyway, you have this y. So you have that equation for y. You can come over here and you can calculate the mass fraction that's diverted for this problem, and it's around 0.17695, 18%. And then 1 minus y, that's what continues on, is 1 minus that value, so it's 0.82305. There you go. There's our 2 values. So we do have those all for all these entries in here. The 1 minus y's are really the ones that are needed. So when we make the multiplication by the, what was it, 82.3%, this value, let me change and type it in, becomes negative 1794.58. And this is still 0, 0, 0. And then this one remains 2727.89, because what went through the steam generator is the same that goes into the first turbine stage. You do the same thing over here. This is still 546.35, but this one is multiplied by that 82.3%, so it's reduced, and so it's a 403.49. Then 0. Multiply by the 1 minus y, and you'll get negative 1.02. And then here you get negative, 15.50 again, because it's the same mass fraction. Okay, now when I do a sum, if I do the sum down here, I'm going to make this bold to emphasize it's the sum. 933.31. That's how much work is out per kilogram that goes through the first turbine stage. It's the net work out in units of kilojoules out of the cycle per kilogram that goes into the first turbine stage. And we come over here, again, this should match, and when you do the math, it does match. So there you go. Now energy is conserved. If they didn't match, look for your error. And sometimes, yes, we'd have to look for our error. So there it is. There's our table of our energy transfers. Now we're ready to solve for part A. I know it's a long way setting it up, but what's the thermal efficiency for this cycle? So our thermal efficiency for the cycle is what, I just put a TH there for thermal, but what is the, it's how much work is out. So the W net divided by what? The Q in, and you only have one place for the Q to come in. And we emphasize this has to be on a same per unit mass basis, so I use my little notation of asterisk. And so it's 933.31 kilojoules per kilogram that goes to the first turbine stage divided by 2727.89. We find the plant's thermal efficiency comes in at 34.2%. Okay, so that's the answer for part A. What about part B? What is the mass flow rate into the first turbine stage in kilograms per second in order for us to get a W dot net of 330 megawatts, or I convert right away to kilowatts. It's just going to save me there you go, 330,000 kilowatts. Well, the equation relating W dot net and W asterisk net is the mass flow rate going into the first turbine stage. So our mass flow rate in the first turbine stage is W dot net divided by W asterisk, lowercase w asterisk net. So this was our 330,000 kilowatts. I'm going to put kilojoule per second. That's just helps a little bit with the units so it's clear. And then what was this one? This one was our 933.31 kilojoules per kilogram. So what you can do is you can do kilojoules goodbye, and then you see it's kilogram, and I should have put first turbine because that's what it is right here, first turbine. And so our answer is the mass flow rate for going into the first turbine turns out to be 353.6 kilograms per second. That's our answer for part B. And the harder one, what about that rate of entropy production in the open feed water heater? And I think maybe I can scoot back here. No, maybe not. Okay, how about back here? Did I not do that entropy balance? Well, I have to do an entropy balance. Let me just make use of this space right in here. Okay, so let's do an entropy balance for this open feed water heater. And so we're going to have the mass flow rate coming down from 2 times the entropy at 2 plus the mass flow rate coming from 5 times the entropy at 5 plus our rate of entropy generation, which we're trying to calculate due to irreversibilities in that open feed water heater, all has to be swept out by the mass flow rate going through 6 times the entropy at 6. We have the S's, S2, S5, and S6. I'm just going to show you. We worked hard to get the S2, the S5, and the S6. All right. How about our mass flow rates? Well, M.6 is the same as what went into the first turbine stage. It's 353.6 kilograms per second. I go back over here and take a look. 353.6 kilograms per second. Now, how about our M.5? Well, that's just 1 minus Y times the 353.6. And likewise, M.2 is just Y times the 353.6. So it's like done, done, done. Only thing we don't know is sigma dot. And you just be careful of the units, and it comes out to be 46.11 kilowatts per Kelvin. And that's the answer for part C. Well, with that, I feel it's a long problem. Hopefully I didn't take too long solving it, and hopefully you get something out of it. Thank you very much for your attention.